Right now, in this very moment, you are experiencing something so fundamental that you never question it. Time is moving forward. You remember your breakfast this morning, but you cannot remember your breakfast tomorrow. You can watch a flower bloom, but you cannot watch it unbloom. Why? Why does time have a direction? Why can we move freely through space but are prisoners marching forward through time? Tonight, we're going to explore one of the deepest mysteries in all of science. A mystery that connects the Big Bang to your morning coffee, quantum particles to the eventual fate of everything. Join me on a journey to understand the arrow of time. Let's begin with a simple observation. You exist in a moment we call now. What is now? It's a strange concept when you really think about it. The past seems fixed and immutable, carved in stone by events that have already happened. The future feels open, pregnant with possibility, containing paths you have not yet taken. And here you are, suspended at the razor's edge between them in this fleeting instant we call the present. This asymmetry between past and future is so deeply woven into your experience that you might never have questioned it. But we should question it, because nothing in the fundamental laws of physics says time must work this way. Consider the laws of motion that govern how particles move, how planets orbit, how galaxies spin. If you could record any of these processes and play the recording backward, the reversed motion would still obey the same laws perfectly. An electron orbiting an atom looks equally valid whether time runs forward or backward. A planet tracing its ellipse around the sun works just as well in reverse. The equations don't care which direction time flows. They are what physicists call time-symmetric. So if the fundamental rules of the universe don't distinguish between past and future, why does your experience of reality have such a clear direction? Why do you age but never grow younger? Why do memories form but never unform? This puzzle has haunted physicists and philosophers for over a century. The laws of nature at their most fundamental level appear reversible. Yet everything you experience is irreversible. You can scramble an egg, but you cannot unscramble it. You can shatter a glass, but the shards will never leap from the floor and reassemble themselves. Perfume spreads through a room, but never spontaneously gathers back into the bottle. Stars burn their fuel, but never unmelt their fused elements back into pure hydrogen. Everywhere you look, you see processes that only go one way, processes that define a direction we call forward. This is the arrow of time, and it points towards something profound. Something called entropy. Before we can understand why time flows, we need to understand what entropy really is. You may have heard it described as disorder or chaos, but that's not quite right. Entropy is better understood as a measure of possibilities. Imagine a bedroom that's perfectly organized. Every book on the shelf, every shirt folded, every item in its designated place. There's essentially one way to achieve this perfect order. But now imagine that same bedroom in a messy state. There are millions of ways the books could be scattered, countless arrangements of rumpled clothes. The messy state has more possible configurations, more ways to arrange the same stuff. That's entropy. It's the number of ways a system can be arranged while still looking essentially the same from the outside. Now, here's the crucial insight. When you have a system that can explore different arrangements randomly, it will naturally tend to spend more time in states with more possible configurations. Not because there's a force pushing it there, but simply because there are more ways to be disorganized than organized. If you shuffle a deck of cards randomly, you're astronomically unlikely to end up with them perfectly sorted by suit and rank. Not because sorting is forbidden, but because there's only one sorted arrangement and trillions of unsorted ones. The system naturally gravitates toward the more probable states. And the more probable states are the ones with higher entropy. This simple statistical tendency is one of the most powerful principles in all of physics. It's the second law of thermodynamics. The second law states that in any closed system, entropy tends to increase over time. Or more precisely, it tends to stay the same or increase, but never decrease. This isn't an absolute rule like conservation of energy. It's a statistical rule. Technically, entropy could decrease. The air molecules in this room could spontaneously gather in one corner, leaving you in a vacuum. But the probability of this happening is so infinitesimally small that you could wait longer than the current age of the universe and never witness it. For all practical purposes, entropy only goes one way. And this one-way tendency of entropy is what gives time its arrow. The direction from lower entropy to higher entropy defines the direction we experience as forward through time. Think about it this way. When you watch a video of a glass shattering, you instantly know which direction is forward in time. You know this because you've never seen the reverse. Shards spontaneously leaping together to form a glass. That's not just unlikely. It's a massive decrease in entropy. The intact glass has relatively low entropy because there's only a narrow range of arrangements where all those molecules form a functioning glass. The shattered pieces have much higher entropy because there are countless ways to arrange those shards. The second law tells us that closed systems evolve from low entropy to high entropy, and so the direction of shattering defines the direction of time. You can use entropy as a clock, an arrow pointing toward the future. So we've identified the arrow. We know that time's direction is tied to entropy's increase. But this raises an even deeper question. If entropy always increases, and if the universe is roughly 14 billion years old, why isn't everything already at maximum entropy? Why isn't the cosmos just a uniform, featureless soup where nothing interesting can happen anymore? Why do we have stars and galaxies and life? Why is there still complexity and structure? The answer is extraordinary. The universe began in a spectacularly low entropy state, and everything interesting that has ever happened, including your existence, is a consequence of entropy climbing from that initial improbable beginning. To understand time's arrow, we must journey back to the beginning of everything. 13.8 billion years ago, everything you see, everything that exists, was compressed into a region smaller than an atom. Not just matter and energy, but space itself. And in this unimaginably tiny, hot, dense state, the universe had extraordinarily low entropy. Now this might seem counterintuitive. How could something so hot and dense be considered organized? Shouldn't that be the definition of chaos? But remember, entropy isn't about temperature or density. It's about the number of possible arrangements. And the early universe, for reasons we're still trying to fully understand, started in one very specific, very improbable arrangement. It was like a tightly wound spring, loaded with the potential to release complexity and structure as it expanded and entropy increased. When the Big Bang occurred, it wasn't an explosion in space. It was an explosion of space. The universe didn't expand into anything. It expanded as a whole, carrying matter and energy with it. And as it expanded, it cooled. The furious energy of the initial moment began to spread out. And here's what's crucial. As the universe expanded and cooled, the maximum possible entropy of the universe increased faster than the actual entropy. Think of it like this. The universe's entropy is going up, following the second law. But the limit, the ceiling of how much entropy could exist given the universe's size and temperature, is rising even faster. This gap between actual and maximum entropy is where all the interesting stuff happens. It's the space where stars can form, where life can emerge, where you can exist. In those first moments after the Big Bang, the universe was a seething plasma of fundamental particles. Quarks, electrons, photons, all bouncing off each other in a furious thermal bath. No atoms could form. It was too hot. The universe was opaque to light. But as expansion continued, things cooled. About 380,000 years after the beginning, the universe had cooled enough for electrons to bind with protons, forming the first atoms of hydrogen and helium. Light could suddenly travel freely. This is the moment we call recombination, and it's the origin of the cosmic microwave background radiation that fills space today. It's the afterglow of creation. And in that afterglow, we can see the seeds of structure, tiny fluctuations in density that would eventually grow into galaxies. Those tiny density fluctuations were quantum in origin. During a brief period called cosmic inflation, microscopic quantum uncertainties were stretched to cosmic scales by the exponential expansion of space. These fluctuations meant that some regions had slightly more matter than others, and gravity amplified these differences. Denser regions pulled in more matter, becoming denser still. Over hundreds of millions of years, these overdense regions collapsed under their own gravity, forming the first stars. These stars were massive, made purely of hydrogen and helium, burning bright and dying young in spectacular supernovas. And in those violent deaths, they forged heavier elements: carbon, oxygen, iron, the building blocks of planets and life. All of this complexity emerging from the initial low entropy state, entropy steadily climbing as structure formed. Here's something remarkable to consider. Every organized structure you see, from galaxies to living cells, exists because the universe is on a journey from low entropy to high entropy. Stars shine because they're converting organized nuclear fuel into disorganized heat and light, increasing entropy. Life exists because it's very good at hastening entropy's increase in its surroundings. You eat organized molecules called food and break them down, using the energy released to maintain your own organized structure while increasing the entropy of your environment. Every breath you take, every thought you think, is part of the universe's relentless march toward equilibrium. You are a temporary eddy in entropy's river, a brief region of order sustained by a surrounding increase in disorder. But why did the universe begin with such low entropy? This is one of the deepest unsolved questions in cosmology. Some theories suggest it's a consequence of how the Big Bang worked, that the initial conditions naturally produced a smooth, uniform, low entropy state. Others propose that our universe is just one bubble in a vast multiverse, and we happen to exist in a region where entropy started low because only such regions can support complex structures like us. This is an application of what's called the anthropic principle. We observe a low entropy beginning because if it weren't low, we wouldn't be here to observe anything. The question remains open, inviting us to wonder and explore further. What we do know is that this initial low entropy state is the ultimate reason time has a direction. If the universe had started in a maximum entropy state, a featureless equilibrium, there would be no arrow of time. Every moment would look like every other. Nothing would change in any meaningful way. There would be no past distinct from the future, no memory, no causation, no story. The fact that you experience time as flowing from past to future is intimately connected to the fact that the Big Bang was a special, organized, low probability event. The universe is still unfolding from that moment, and every tick of every clock measures entropy's patient accumulation. Time's arrow was notched in the first instant of creation and has been flying forward ever since. Now, let's explore something strange about gravity and entropy. You might think that when things are spread out evenly, that's high entropy. And generally, that's true. Gas molecules evenly distributed in a room have higher entropy than molecules concentrated in one corner. But gravity flips this intuition on its head. For gravitating systems, the uniform state is actually low entropy. A gas cloud spread evenly through space is organized. Wait, it's unstable. Gravity wants it to clump together. And when it does clump, forming stars and galaxies, that's entropy increasing. This seems backward, but it makes sense when you think about it. A clumped state has more ways to arrange individual particles while maintaining the same overall clumpy appearance. Gravity makes the clustered state more probable than the smooth state. This is why the universe has become increasingly clumpy over time, even as entropy increases. The early universe was remarkably smooth. Small fluctuations existed, but matter was spread relatively evenly. As time marched forward, gravity pulled matter together. Gas clouds collapsed into galaxies. Within galaxies, clouds collapsed into stars. Some stars collapsed into black holes. Each of these collapses represents entropy increasing, even though it looks like we're creating order from chaos. The galaxy is more organized than the cloud that made it, true. But the configuration space, the number of ways particles can be arranged within that galaxy while maintaining its structure, is vastly larger than the configurations available to the smooth cloud. Gravity rewards clumping with entropy. Black holes are the ultimate expression of gravity's relationship with entropy. When a massive star collapses, it can become so dense that space-time itself curves to the point of no return. An event horizon forms, a boundary beyond which nothing, not even light, can escape. From the outside, a black hole appears to be the simplest object possible. It's defined by just 3 properties: mass, charge, and spin. You might think this simplicity means low entropy, but physicist Stephen Hawking and his colleague Jacob Bekenstein discovered something astonishing. Black holes have enormous entropy, proportional to the area of their event horizon. A stellar mass black hole has more entropy than all the particles that collapse to form it. Black holes are entropy monsters. Here's why this matters for time's arrow. When matter falls into a black hole, the information about that matter seems to disappear. A book, a person, a star. Once it crosses the event horizon, from our perspective outside, all the detailed information about what fell in is lost. Only the black hole's mass, charge, and spin change. This apparent loss of information troubled physicists deeply because information loss would violate quantum mechanics. The paradox may be resolved by understanding that information is somehow encoded on the event horizon itself, preserved in a way we don't fully understand yet. But regardless of how the paradox resolves, black holes represent a one-way process. Matter and energy go in, entropy increases, time marches forward. Nothing comes back out. At least, not in any recognizable form. Hawking later showed that black holes aren't completely black. Due to quantum effects near the event horizon, they emit radiation. This Hawking radiation means black holes very slowly evaporate over immense timescales. But eventually it would vanish, converting its mass into thermal radiation spread across space. This radiation is essentially featureless, maximum entropy. When a black hole finally evaporates, the entropy of the universe has increased dramatically. And here's the thing, that process is irreversible. You cannot gather that radiation back together and reconstruct the black hole, let alone the star that formed it, or the gas cloud that formed the star. Time's arrow flies straight and true, so gravity, which seems to create order by forming stars and galaxies, is actually the universe's way of maximizing entropy. Every star that forms burns its fuel irreversibly. Every galaxy that assembles will eventually exhaust its star-forming gas. Every black hole that forms will eventually evaporate. The magnificent structures we see in space are not defying entropy. They are manifestations of entropy, increasing in the only way it can in a universe governed by gravity. Structure forms because it's the path to disorder. Beauty emerges because the universe is forgetting its organized beginning. And all of this gives time its forward direction. The universe is getting older, more spread out, more entropic, and there's no going back. Yet in this cosmic forgetting, in this increase of entropy, lies the possibility of everything we value. Memory requires a difference between past and future. Cause requires time's arrow. Life requires the flow of energy from low to high entropy. Thought requires the same. Without entropy increasing, without time flowing forward, the universe would be timeless, changeless, and utterly empty of meaning or experience. The arrow of time might seem like a constraint, a prison march toward an inevitable heat death. But it's also the foundation of causality, agency, and existence itself. We should not mourn time's direction. We should stand in awe of it, because that direction is what allows us to stand at all. Let's return now to the thermodynamic arrow of time, the most familiar and immediate way we experience time's direction. This is the arrow defined by the second law of thermodynamics. Heat flows from hot to cold. Coffee cools down, never spontaneously heats up. Ice cubes melt in your drink, never form spontaneously from water. These everyday experiences are all manifestations of entropy, increasing in closed systems. And they're irreversible, at least in practice. You could, in principle, make ice cubes by removing heat from water. But doing so requires work, requires energy input from somewhere else. And when you account for the full system, including the refrigerator and the power plant generating its electricity, total entropy still increases. There's no escaping the second law. The thermodynamic arrow is so powerful because it applies to everything with many particles. It's a statistical law arising from the sheer number of ways particles can be arranged. Consider a bottle of perfume opened in a corner of a room. The perfume molecules start concentrated in one spot. Then they spread out, bouncing off air molecules randomly until they're distributed throughout the room. This spreading happens because there are vastly more ways for the molecules to be spread out than concentrated. The number of concentrated arrangements is tiny compared to the number of spread out arrangements. So the system naturally evolves toward the spread out state. And once spread out, it never spontaneously reconcentrates. That would be an entropy decrease, and it's staggeringly unlikely. What about life? Living things seem to defy entropy. You grew from a single cell into a complex organism with trillions of specialized cells. That's a massive increase in organization. Plants build complex molecules from simple ones using sunlight. How is this compatible with entropy always increasing? The answer is that living things are not closed systems. They're open systems that maintain their low entropy by increasing the entropy of their surroundings even more. You consume food, which is organized matter and energy. You break it down, use it, and release waste heat and simple molecules back into your environment. The entropy you create in your surroundings exceeds the entropy, decrease you achieve in yourself. Life surfs the entropy gradient, maintaining order locally by generating disorder globally. Photosynthesis is a perfect example. A plant captures photons from the sun, organized packets of energy, and uses them to build complex sugar molecules from carbon dioxide and water. The sugars are low entropy, highly organized. But the plant releases heat and the sun itself burns fuel irreversibly, converting organized nuclear energy into disorganized light and heat. When you factor in the sun, the total entropy of the system increases enormously. The plant is just a local entropy decreasing machine powered by a much larger entropy increasing machine. The second law holds. And this connection between life and entropy reveals something profound. Life is not fighting against the arrow of time. Life is absolutely dependent on it. Without entropy increase, without a flow from order to disorder, there would be no energy gradients to exploit. No basis for metabolism, no life. The thermodynamic arrow connects intimately to our psychological arrow. Your brain forms memories by creating physical changes in neural connections. These changes are records, low entropy structures that encode information about past events. But forming a memory requires energy. Your neurons consume glucose and oxygen, generating heat and waste. Creating a memory increases entropy overall, even as it creates a localized record. And memories decay over time. The neural connections gradually degrade, fade, become unreliable. This is entropy at work in your mind. The past becomes increasingly fuzzy, not because of some arbitrary rule, but because maintaining perfect records would violate thermodynamics. Forgetting is entropy. Remembering is a temporary decrease paid for by a surrounding increase. Your mind is proof of time's arrow. Even the computers we build obey the thermodynamic arrow. Every computation has an energy cost. Every bit of information written to memory increases entropy, somewhere in the form of waste heat. The Landauer principle tells us there's a fundamental minimum energy cost to erasing information, and that cost is paid in entropy. This means that even in a perfectly efficient computer, computation generates heat, contributes to entropy, and requires an arrow of time. The reason your laptop gets warm is the same reason you age. Both are consequences of the second law. Both are manifestations of the universe's journey from the Big Bang's low entropy toward an eventual maximum entropy, heat death. Every calculation, every thought, every memory pushes us further along time's arrow, so the thermodynamic arrow is not just some abstract physics concept. It's the reason your coffee cools. It's why you age. It's why you remember yesterday but not tomorrow. It's why your brain works at all. Every chemical reaction in your body, every firing of every neuron, every beat of your heart is an irreversible process that increases entropy. You are a thermodynamic phenomenon, a pattern that temporarily resists the drift toward equilibrium by increasing entropy in your surroundings. And the same is true of stars, galaxies, and the universe itself. Everything that happens because entropy can increase by happening. The thermodynamic arrow is the master arrow, the one from which all other arrows emerge. It is time itself, flowing inexorably from past to future. Now, let's venture into the strange world of quantum mechanics and ask how time's arrow manifests at the smallest scales. Quantum mechanics is famously weird. Particles can be in multiple states at once, described by a wave function that evolves smoothly and deterministically according to the Schrödinger equation. This evolution is perfectly time-symmetric. If you run the Schrödinger equation backward, you get a valid solution. A quantum particle's wave function can spread out and then converge back to its starting point. At the quantum level, the fundamental dynamics are reversible. So where does the arrow of time come from in quantum mechanics? The answer has to do with measurement, with observation, with what happens when the quantum world interacts with the classical world. When you measure a quantum system, something peculiar happens. The wave function collapses. Before measurement, an electron might be in a superposition. existing in multiple locations at once. But the instant you measure it, you find it in one definite location. The superposition vanishes, replaced by a single, definite outcome. This collapse is irreversible and non-deterministic. You can't uncollapse a wave function. And you can't predict with certainty which outcome you'll get, only the probabilities of different outcomes. Many physicists argue that measurement is where time asymmetry enters quantum mechanics. The smooth, reversible evolution of the wave function gives way to the abrupt, irreversible collapse. And collapse always goes in one direction, from superposition to definite state, from quantum to classical. But what is measurement really? This is one of the deepest questions in quantum mechanics. Some interpretations say that measurement is a special process, a fundamental feature of reality that introduces irreversibility. Others say there's no collapse at all. In the many worlds interpretation, the wave function never collapses. Instead, each possible outcome occurs in a different branch of reality. When you measure the electron, the universe splits. You in one branch see it here. You in another branch see it there. In this view, the evolution remains reversible at a cosmic level. But any individual observer experiences an arrow of time because they only have access to one branch. They can't access the other branches to reverse the process. The subjective experience of time is built into the branching structure. Another way to think about quantum time asymmetry is through decoherence. When a quantum system interacts with its environment, which is made of countless particles, the environment acts like a continuous measurement. The system becomes entangled with the environment, and this entanglement causes the quantum superposition to effectively disappear from the perspective of any observer in the system. The information about the superposition gets spread out into the environment, becoming inaccessible. This is decoherence, and it's irreversible because recovering the information would require tracking every particle in the environment. Decoherence explains why large objects like cats and people don't appear in superpositions. We're constantly decohering, and decoherence is an entropy increase. The information spreads out. The arrow of time emerges. What's fascinating is that decoherence is essentially a thermodynamic process. It's entropy increasing at the quantum level. A pure quantum state has low entropy. It's a specific configuration of the wave function. As the state becomes entangled with the environment and decoheres, entropy increases. The system transitions from a low entropy pure state to a high entropy mixed state. So even in quantum mechanics, the arrow of time is connected to entropy. The second law reaches down to the quantum realm, and this means the quantum arrow and the thermodynamic arrow are not separate. They're manifestations of the same underlying principle. The universe evolves from low entropy to high entropy at every scale, from the Big Bang to quantum measurements. Entropy is the universal clock. There's also something called the quantum Zeno effect, which reveals another aspect of time in quantum mechanics. If you repeatedly measure a quantum system very frequently, you can actually freeze its evolution. The wave function keeps collapsing before it has a chance to evolve. It's as if measurement pins the system in place, preventing change. This is time asymmetry at work. The measurements are irreversible interventions that alter the natural evolution. And they can't be undone. That you can't unmeasure. This effect has been demonstrated in experiments. By observing a quantum system continuously, physicists can prevent it from decaying or changing states. But this requires a constant input of measurement energy, and that measurement increases entropy elsewhere. You're not stopping time. You're just converting quantum evolution into thermodynamic irreversibility. So even at the quantum scale, time has an arrow. It might emerge from measurement, from decoherence, from entanglement with the environment. play? It's there. The microscopic world is not some reversible clockwork beneath our irreversible macroscopic experience. The irreversibility goes all the way down. From quarks to galaxies, from wave functions to the expansion of the cosmos, time flows forward. And that flow is intimately connected to entropy, to information, to the structure of reality itself. We can't reverse time any more than we can unbreak a glass or unthink a thought. The arrow is woven into the fabric of existence, and understanding this helps us see that time is not an illusion or an emergent approximation. Time is real, and its direction is fundamental. Let's zoom out now to the largest scales and explore the cosmological arrow of time. This is the arrow defined by the expansion of the universe itself. The universe is getting bigger. Galaxies are moving apart. Space itself is stretching. And this expansion is a one-way process. The universe has never been observed to contract. In fact, we've discovered that the expansion is accelerating, driven by something we call dark energy. This cosmic expansion gives time a clear direction, the direction of increasing separation, the direction away from the Big Bang. The universe at any given moment is larger than it was before and smaller than it will be. And this provides a cosmic clock, a way to measure time that applies to the entire universe. The arrow of expansion, the discovery that the universe is expanding, came from Edwin Hubble in the 1920s. He observed that distant galaxies are redshifted, meaning their light is stretched to longer, redder wavelengths. The farther the galaxy, the greater the redshift. This is not because galaxies are moving through space away from us. It's because space itself is expanding, carrying the galaxies with it. As light travels through expanding space, it gets stretched. The wavelength increases, and this stretching is proportional to distance. Hubble's law connects distance and recession velocity, and it implies that if we run the expansion backward in time, everything converges to a point. Big Bang. The beginning. The moment when the cosmological arrow was set in motion. The expansion of the universe is described by general relativity, Einstein's theory of gravity and space-time. In this theory, matter and energy tell space-time how to curve, and curved space-time tells matter how to move. The universe's expansion emerges from the equations when you apply them to the cosmos as a whole. And here's something subtle but important. The expansion is not driven by the Big Bang in the sense of an explosion pushing things outward. Rather, it's a consequence of the initial conditions and the dynamics of space-time itself. The universe doesn't expand into anything. It's not like a balloon inflating in a room. The universe is all there is. Space itself is growing. And this growth is the cosmological arrow, inseparable from the flow of time. You might wonder if the cosmological arrow is the same as the thermodynamic arrow. The answer is they're deeply connected but not identical. The expansion creates the conditions for entropy to increase. As the universe expands and cools, it moves away from thermal equilibrium. This allows structures to form, stars to burn, life to emerge. All of these are entropy-increasing processes enabled by expansion. If the universe were static and already at maximum entropy, nothing would happen. There would be no change, no time. The expansion provides the stage on which entropy's drama plays out. And because both arrows point in the same direction, from the Big Bang onward, they reinforce each other. Expansion and entropy increase are two sides of the same cosmic coin. In 1998, astronomers made a stunning discovery. The universe's expansion is not slowing down as many expected. It's accelerating. Distant supernovae are farther away than they should be if expansion were constant or decelerating. Something is pushing space apart, counteracting gravity. We call this mysterious something dark energy, and it makes up about 68% of the universe's total energy content. We don't know what dark energy is. It might be a property of space itself, a cosmological constant, or it might be a dynamic field that changes over time. But whatever it is, it means the universe will expand forever, faster and faster. The cosmological arrow will never reverse. There will be no big crunch, no collapse back to a singularity, only eternal expansion. What does eternal expansion mean for time's arrow? It means the thermodynamic arrow will also continue indefinitely. Entropy will keep increasing. Stars will exhaust their fuel. Galaxies will drift apart beyond the reach of each other's light. New star formation will cease as gas is depleted. Eventually, in trillions of years, all stars will die. White dwarfs, neutron stars, black holes will be all that remain. Then, over incomprehensibly long timescales, even black holes will evaporate via Hawking radiation. In the end, the universe will approach a state called heat death, maximum entropy. Thermal equilibrium. A vast, cold, dark expanse where nothing changes. And in that far future, there will be no arrow of time because there will be no gradients, no structure, no change. Time will still exist, but it will have lost its meaning. But we're not there yet. We're living in what cosmologists call the stelliferous era, the age of stars. This is a golden age, a brief window in cosmic history when the universe is structured and interesting. When entropy is high enough for complexity but not so high that everything has reached equilibrium. We exist during the only time in the universe's history when galaxies shine and life can emerge. Before us was the dark age, before stars formed. After us will be the long darkness of heat death. We are privileged to live when the arrow of time is flying through its most vibrant arc. The cosmological arrow, the thermodynamic arrow, and our own psychological arrows all align, all point forward, all tell the same story. Time is moving from the Big Bang toward the end. And we are passengers on that journey. Now, let's explore the most intimate arrow of time, the psychological arrow. This is your subjective experience of time flowing from past to future. You remember the past. You experience the present. You anticipate the future. This asymmetry is so fundamental to consciousness that it's hard to imagine existing without it. But why do you experience time this way? Is the psychological arrow a consequence of the other arrows, or is it something separate? The answer seems to be that your psychological arrow is grounded in the thermodynamic and cosmological arrows. Your brain is a physical system that obeys the laws of thermodynamics. Memory formation requires entropy, increase. Thought requires energy flow. Your experience of time is a reflection of the universe's fundamental asymmetry. Memory is key to understanding the psychological arrow. You have records of the past stored in your brain, neural connections that encode information about events that have happened. These records allow you to distinguish past from future. You know what happened yesterday because you have memories. You don't know what will happen tomorrow because you have no memories of it. But creating and maintaining memories requires energy. Every memory formed involves chemical and electrical changes in neurons, processes that increase entropy. And memories decay over time. Old memories fade or become distorted. This is not a bug. It's thermodynamics. Perfect records would require infinite energy to maintain. Forgetting is the price of remembering. And both processes define time's direction in your mind. There's a fascinating thought experiment about memory and time. Imagine a universe running in reverse. All the physical processes reversed. Stars unburning their fuel. Broken glasses reassembling. Now imagine a person in this reversed universe. Would they experience time running backward? The surprising answer is no. Their memories would also be running in reverse. They would forget the future and remember the past relative to the physical arrow. To them, time would still feel like it's flowing forward because their psychological arrow would still align with the thermodynamic arrow of their universe. The direction of memory formation determines the psychological arrow, and memory formation is always in the direction of entropy increase. Your experience of time is not independent of physics. It's embedded in physics. What about anticipation? You can't remember the future, but you can anticipate it. You can make predictions based on patterns and cause and effect, but your predictions are always uncertain. The future is open in a way the past is not. Or is it? According to physics, the future might be just as determined as the past. If you knew the exact state of every particle in the universe and had infinite computational power, you could, in principle, calculate what happens next. The future would be determined. But you don't have that knowledge. You have limited information and limited computational resources. So to you, the future is unknown and uncertain. The openness of the future might be epistemological, not fundamental. It's about what you can know, not about what is. This brings us to the question of free will and time. If the future is determined, are your choices real or illusory? This is a deep philosophical question without a clear answer. But here's one perspective. Even if the future is determined by the laws of physics and the past state of the universe, you don't have access to that information. You can't see the determined future. You experience choice because you're operating with incomplete information, navigating a landscape of possibilities that narrow as you make decisions. Your sense of agency, your experience of choosing, is real even if the outcome was in some sense predetermined. And this experience is intimately tied to time's arrow. You deliberate about the future, not the past. You feel agency over what comes next, not what came before. There's also the perception of time's passage. You don't just know that time has passed. You feel it passing. Moments seem to flow. The present feels like it's moving forward through time. But is this flow real or illusory? Some philosophers argue that time doesn't actually flow. The past, present, and future all exist equally in what's called the block universe view. Time is like space, a dimension you can move through, but all moments exist simultaneously. The flow is an illusion created by your consciousness. Others argue that the present is special, that only now exists, and the flow is real. This debate is unresolved. But either way, your experience of flow is connected to memory, causation, and entropy. The psychological arrow feels like a flow because your brain is constantly updating, constantly processing, constantly marching toward higher entropy. Ultimately, the psychological arrow is the most personal way we experience time's asymmetry. It's how you know who you are, where you've been, what you hope to become. Without it, there would be no narrative, no self, no story. Your identity is built from memories, stretching from past to present. And your sense of meaning comes from projects and goals that stretch from present to future. The arrow of time isn't just a physical law. It's the architecture of your mind. It's how you experience reality. And recognizing this connection between the physics of entropy and the phenomenology of consciousness is profound. You are not separate from the universe. You are a pattern within it, experiencing its asymmetry from the inside. Time flows through you just as it flows through stars and galaxies. You are time becoming aware of itself. Let's consider a strange question. Could time's arrow ever reverse? Could entropy start decreasing instead of increasing? Could the future become the past and the past become the future? At first, this seems absurd. We've spent this entire journey establishing that entropy increase is not just probable, but overwhelming. The second law is one of the most ironclad principles in physics. But let's entertain the possibility. If we waited long enough, could random fluctuations cause entropy to spontaneously decrease? The answer is technically yes, but in practice, no. The timescales involved are so astronomically long that they defy imagination. We're talking about far longer than the age of the universe, far longer than the time until heat death, essentially infinite for all practical purposes. There's a concept called Poincare recurrence that says if you have a closed system and wait long enough, it will eventually return to a state very close to its initial state. This is a mathematical theorem. It applies to systems with reversible dynamics. So if you have a box of gas and wait an incomprehensibly long time, the gas molecules will eventually return to their initial positions. Entropy will have completed a cycle, but the time required is something like 10 to the power of 10 to the power of 100 years. Number so large you can't write it in normal notation. For comparison, the universe is only about 10 to the 14 years old. Poincare recurrence is real in theory, but irrelevant in practice. The arrow of time is effectively permanent. Another scenario involves what are called Boltzmann brains. This is a thought experiment proposed by the physicist Ludwig Boltzmann. If you wait long enough in a high entropy universe, random thermal fluctuations could spontaneously assemble a structure as complex as a brain, complete with memories and thoughts. This Boltzmann brain would exist briefly before dissipating back into the thermal chaos. And here's the weird part. In a sufficiently old universe, these random brains would vastly outnumber real brains that evolved through the thermodynamic arrow. Most conscious observers would be Boltzmann brains with false memories popping into existence for a moment. This is deeply unsettling. It suggests our memories might be unreliable if the universe is old enough. But most physicists think this is more of a reductio ad absurdum, suggesting something is wrong with our assumptions about the very late universe. What if the universe is cyclical? What if instead of expanding forever, it eventually stops and contracts, ending in a big crunch, and then bounces, creating a new Big Bang? In such a cyclical universe, would time's arrow reverse during the contraction phase? Would entropy start decreasing? Most models say no. Even during contraction, entropy would continue to increase. The arrow of time would still point away from the bounce, not toward it. Contraction doesn't reverse thermodynamics. It just changes the expansion rate. The future would still be higher entropy than the past. However, some exotic models suggest the arrow could flip during a bounce, creating a symmetry where time runs backward in the contracting phase. These models are highly speculative and not widely accepted, but they're fascinating to consider. There's also the possibility of localized entropy decreases in the far future. After heat death, in a universe at maximum entropy, random quantum fluctuations would still occur. These fluctuations could, in principle, create tiny regions where entropy temporarily decreases. Perhaps a small patch of space spontaneously organizes into a star or a planet. These would be incredibly rare and short-lived. But given infinite time, they would happen. And within one of these fluctuation regions, you could have temporary structure, temporary complexity, a brief reprieve from the featureless equilibrium. But this doesn't represent a reversal of the arrow of time for the universe as a whole. It's just a local fluctuation in an otherwise maximum entropy state. The overall arrow still points toward disorder, always. So the answer to whether time could reverse is complicated. In theory, under absurdly specific and improbable conditions, or over timescales that dwarf the age of the universe by unimaginable factors, entropy could decrease. Poincaré recurrence could return a system to a low entropy state. But for all practical purposes, for any timescale relevant to humans or stars or galaxies or even the observable universe's lifetime, the arrow of time is fixed. Entropy increases. Time flows forward. The past is gone, the future is ahead, and you're moving through the present at 1 second per second. The arrow is permanent because the initial conditions of the Big Bang were so improbable, and the statistical weight of high entropy is so overwhelming. Time is a one-way street, and we're all traveling down it together. Even if we could reverse entropy locally, using advanced technology to create a region of decreasing entropy, we would pay for it elsewhere. Building such a system would require energy and computation, increasing entropy in the surroundings. Maxwell's demon, a thought experiment about a tiny being who sorts molecules to decrease entropy, was ultimately shown to be impossible without increasing entropy elsewhere. Every attempt to reverse the arrow locally just reinforces it globally. The second law is inescapable, and this inescapability is not a limitation. It's a feature. It's what makes causality work. It's what makes memory possible. It's what gives time meaning. Without the arrow, the universe would be a static, timeless void. With the arrow, we have stories, experiences, change, growth, and meaning. The arrow of time is the spine of reality. And we should embrace it. Let's explore how time behaves at the extremes of the universe. Near black holes, time becomes profoundly strange. Einstein's general relativity tells us that massive objects warp space-time, and this warping affects the flow of time itself. Near a black hole's event horizon, time slows down dramatically compared to regions farther away. An observer watching someone fall into a black hole would see them slow to a crawl, never quite crossing the horizon, frozen in time by extreme gravity. Meanwhile, the falling person would experience time normally, crossing the horizon and reaching the singularity in finite time. Time is relative. Its rate depends on where you are in the gravitational field, and this relativity is intimately connected to entropy and information. At the singularity inside a black hole, general relativity breaks down. Time and space become meaningless. The curvature becomes infinite. The equations produce nonsense. We need a theory of quantum gravity to understand what really happens there. String theory, loop quantum gravity, and other approaches attempt to describe this regime, but we don't yet have a complete answer. What we do know is that the singularity represents an extreme of time's arrow. Once you cross the event horizon, all paths lead to the singularity. You're moving through time toward an endpoint where time itself might cease to have meaning. The arrow of time becomes a trajectory you cannot escape. It's the ultimate one-way journey. And it ends in a place where our current understanding of physics fails. At the other extreme, consider the Planck scale. This is the realm of the very small and very energetic, where quantum mechanics and gravity both become important. The Planck time is about 10 to the minus 43 seconds. This is the smallest meaningful unit of time according to our current theories. Below this scale, the concept of time as a smooth continuum might break down. Space and time might become granular, discrete, quantized. Some theories suggest that at the Planck scale, space-time is a foam of quantum fluctuations, constantly bubbling with virtual particles and topology changes. In this regime, the arrow of time might emerge from something more fundamental. Perhaps causality and temporal order arise from quantum entanglement or information flow at the most basic level. There's also the beginning of time itself. What happened at the Big Bang? Was there time before the Big Bang? These questions push the limits of cosmology. Some models suggest the Big Bang was the beginning of time. Before it, there was no before. Time itself came into existence with the universe. Other models suggest our Big Bang was a transition from a previous state, perhaps a previous universe that contracted and bounced. In these cyclical models, time extends infinitely into the past and future. Still, other models invoke quantum mechanics to blur the concept of a beginning. In quantum cosmology, the universe might have no definite starting point, instead existing in a superposition of histories. The arrow of time might emerge from this quantum foam as the universe becomes classical. Another extreme is the heat-death far future. When the universe reaches maximum entropy, will time still exist? The answer is subtle. Time as a dimension of space-time will still exist according to relativity, but time as a marker of change might become meaningless. If the universe is in perfect thermal equilibrium, every moment looks like every other. There's no way to distinguish past from future. No arrow. No arrow. No change. Time would still pass in the sense that the space-time manifold extends, but nothing would happen. It would be like a frozen eternity. Some physicists speculate that consciousness could not exist in such a state because consciousness requires change, requires information processing, requires the flow of entropy. The arrow of time and the possibility of experience are linked. Time also behaves strangely in the context of cosmic inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, space expanded faster than light. This doesn't violate relativity because it's space itself expanding, not things moving through space. But it has implications for causality and time. Regions of space that are now far apart were once in causal contact, but inflation stretched them beyond each other's horizons. They can no longer influence each other. The arrow of time in one region is independent of the arrow in another. They're causally disconnected. This raises questions about whether time is universal or local. Is there one cosmic time for the whole universe, or many separate times for different regions? The answer depends on the details of cosmology and remains an open question. At all these extremes, black holes, the Planck scale, the Big Bang, the heat death, inflation, time reveals itself as more complex and stranger than our everyday experience suggests. It's not just a simple ticking clock. It's woven into the structure of space-time, connected to gravity, entropy, quantum mechanics, and information. Understanding time requires understanding all of physics. And conversely, understanding physics requires understanding time. The arrow of time is not separate from the laws of nature. It's embedded in them. And as we probe the extremes, we're learning that time itself might be emergent, arising from something more fundamental. Perhaps the deepest question in physics is not what time is, but why there is time at all. And that question remains beautifully open. After exploring the physics and cosmology of time's arrow, let's return to the personal. What does it mean for you in your daily life that time only moves forward? How should you relate to this fundamental asymmetry? One response is acceptance. Time's arrow is not something you can change or escape. Wouch, you age. Opportunities pass. The mistakes are permanent. But this irreversibility is also what makes moments precious. If time were reversible, nothing would matter. Every choice could be undone, every experience repeated infinitely. The arrow of time gives weight to your actions. It makes now important. It makes your choices real. Accepting the arrow means accepting that life is finite, unrepeatable, and therefore meaningful. Each moment exists once and then becomes part of the unchangeable past. There's a concept in physics called the time scale of equilibration. This is how long it takes a system to reach maximum entropy. For a cup of coffee, it's minutes. For a star, it's billions of years. For the universe, it might be googol's of years. You exist on a much shorter timescale. Your life is measured in decades. This means you're living in a universe that, from your perspective, is far from equilibrium. There's still a long way for entropy to climb, and this gap between current and maximum entropy is the space where your life happens. You eat, think, love, create, all by riding the entropy gradient. Your existence is a temporary eddy in the cosmic flow toward disorder. And recognizing this can be humbling and inspiring. Time's arrow can change how you think about memory and nostalgia. Nostalgia is a longing for the past, a desire to return to what was. But the arrow of time makes this impossible. The past is fixed. It cannot be revisited or changed. Photos and memories are traces, echoes of what was, but the moments themselves are gone forever. It can feel sad, but it also means that the past, precisely because it's unreachable, has a kind of permanence. It exists as part of your history, shaping who you are now. And the future, precisely because it's open, invites you to create new moments. The arrow doesn't trap you in the past. It propels you toward the future. And this forward motion is where hope and possibility live. The arrow of time also relates to regret and forgiveness. When you make a mistake, you cannot unmake it. The egg is scrambled. The words are spoken. The action is taken. This can lead to regret, to wishing you could go back and choose differently. But the arrow of time teaches that backward is not an option. The only direction is forward. And moving forward means learning, growing, and when appropriate, seeking or offering forgiveness. Forgiveness is an acknowledgement of the arrow. It says, that was then, this is now, and we can only move forward from here. It's a way of making peace with irreversibility. The past shapes you, but it doesn't have to imprison you. The arrow points ahead. There's also a relationship between the arrow of time and meaning. Many philosophers argue that mortality, the fact that life ends, is what gives life significance. If you lived forever, if time stretched infinitely in both directions, would anything matter? Would you value relationships, experiences, accomplishments? The arrow of time, by making life finite, makes it precious. You have limited time, and this limitation forces you to choose what matters. It creates urgency and value. Every sunset is special because you'll only see finitely many. Every conversation with a loved one is meaningful because time together is limited. The arrow of time is the source of both loss and meaning, and embracing this duality is part of wisdom. Living with the arrow also means accepting change. Nothing stays the same. Your body changes. Your relationships evolve. The world around you transforms. This can be uncomfortable. Humans often desire stability and permanence, but the arrow of time makes change inevitable. And while this brings loss, it also brings growth. You are not the same person you were 10 years ago, and 10 years from now you'll be different again. This constant becoming, this evolution through time, is not something to resist. It's the nature of existence in an entropic universe. Embracing change means aligning yourself with time's arrow rather than fighting against it. It means flowing with the current rather than struggling upstream against an unstoppable force. And finally, understanding the arrow of time connects you to the cosmos. You are not separate from the universe. You are part of it, made of atoms forged in stars, governed by the same laws of thermodynamics that shape galaxies. Your arrow of time is the universe's arrow. When you age, when you remember, when you act and cause effects, you are participating in the cosmic journey from the Big Bang toward heat death. This might sound bleak, but I find it profound. You are a way for the universe to experience itself, to know itself. Your consciousness is time becoming aware of its own flow. And in that awareness there is beauty, wonder, and meaning. The arrow of time is not your enemy. It's the stage on which your life unfolds. And that stage is vast, ancient, and magnificent. We've journeyed through entropy, cosmology, quantum mechanics, and consciousness. We've explored why time has a direction and what that direction means. But for all we've learned, deep mysteries remain. Why did the universe begin in such a low entropy state? This is perhaps the most fundamental question. If the early universe had started in a high entropy equilibrium, there would be no arrow, no structure, no life. But it didn't. It started organized, and we don't fully know why. Some theories point to cosmic inflation, others to quantum gravity effects, still others to the multiverse, but we don't have a definitive answer. The arrow of time is built on a foundation that we're still excavating, and this should fill you with wonder. The deepest questions remain open. Another mystery is the relationship between time and consciousness. We know that our experience of time is connected to memory and entropy. But is consciousness necessary for time to have meaning? Would there be an arrow of time in a universe without observers? Most physicists say yes. Entropy would increase, stars would burn, galaxies would form, all without anyone watching. The arrow is objective. But some interpretations of quantum mechanics suggest that observation plays a fundamental role. That the collapse of the wave function, which is time asymmetric, requires measurement. And measurement might require consciousness. This is deeply controversial, but it raises the possibility that consciousness and time are more intimately connected than we realize. Perhaps time is not just something we experience. Perhaps we, in some sense, participate in creating it. There's also the mystery of time's fundamental nature. Is time a dimension like space, as relativity suggests? Or is it something different, more fundamental? Some theories, like loop quantum gravity, suggest that space and time are emergent. They arise from a more basic quantum structure. In these theories, at the deepest level, there is no smooth space-time. There are discrete quanta of geometry, a network of relationships. Time emerges from changes in this network. If this is true, then the arrow of time might also be emergent, arising from how information flows through the quantum network. Time would not be fundamental. It would be derived. This is a radical idea, and it's not yet proven. But it hints that the mystery of time is even deeper than we thought. Another open question is whether the laws of physics are truly time-symmetric or whether there's a fundamental asymmetry we haven't discovered yet. We know the second law introduces a statistical asymmetry, but are the underlying laws themselves time-symmetric? Most are, but there's an exception. Certain weak nuclear interactions violate what's called CP symmetry, and when you combine this with other symmetries, it implies a small violation of time reversal symmetry. This is called CPT violation or T violation. It's been observed experimentally, but it's very weak. Does this small asymmetry at the particle level connect to the large-scale arrow of time, or is it a separate phenomenon? We don't know. It's possible that time asymmetry goes all the way down, that the universe, at its most fundamental level, distinguishes past from future. What about time travel? Is it possible to move backward through time, to reverse the arrow? General relativity allows solutions with closed time-like curves, paths through spacetime that loop back on themselves. These are wormholes and other exotic structures. In principle, they permit time travel, but they require negative energy or exotic matter that we've never observed. And even if they exist, they raise paradoxes. If you travel back and prevent your past self from time traveling, what happens? Most physicists think these paradoxes suggest time travel is impossible, that some as yet unknown law of physics prevents it. But we don't know for sure. The arrow of time might be unbreakable by law, or it might just be unbreakable in practice. The mystery remains. There's a philosophical question too. Is the arrow of time real or subjective? We've argued it's real, grounded in entropy and cosmology, but some philosophers take a different view. They argue that past, present, and future are equally real, that the flow of time is an illusion created by consciousness. In this view, called the block universe or eternalism, all moments exist simultaneously in a four-dimensional space-time. The arrow is just the perspective of conscious beings moving through this block. The universe doesn't change. It simply is. We experience change because our consciousness traces a path through the unchanging whole. This view is compatible with relativity but challenges our intuition deeply. It suggests that right now, in some sense, all moments of your life coexist. That time doesn't flow. It just is. And you move through it. We've learned a lot. We know entropy increases. We know the universe expands. We know memory forms in one direction. But we don't fully know why it started this way or whether it could be different. We don't know if time is fundamental or emergent. We don't know how consciousness fits in. These mysteries are not frustrations. They're invitations. Invitations to wonder, to explore, to question. The arrow of time is one of the universe's deepest features. And the fact that we can contemplate it, study it, write hour-long documentaries about it is itself profound. We are time-made conscious. And in our questioning, in our wondering, we're participating in the universe's attempt to understand itself. The mystery remains. And that's beautiful. Our journey through time's arrow is complete. We've traveled from the Big Bang to the heat death, from quantum mechanics to black holes, from the cosmos to your own consciousness. We've seen that time's directionality is not arbitrary. It emerges from entropy, from the low entropy beginning of the universe. It's woven into every process, from the burning of stars to the formation of your memories. And it's what makes existence meaningful. Without the arrow, there would be no stories, no change, no life. So the next time you feel time slipping away, remember that this flow is not something to fear. It's the foundation of everything you are. You are a temporary pattern in the cosmic journey from order to disorder. And in that temporary existence, you have the privilege of awareness, of wonder, of choice. Time flows, and you flow with it. Until we meet again, may you find peace in time's passage and meaning in its direction.